In this example, we're going to conserve momentum in order to propel a sled off of a lake of ice that is very smooth, no friction. So we have Sarah here with a dilemma. Sarah's out in the middle of a lake. We won't say how Sarah got there. It's a physics problem. So Sarah's out in the middle of a lake on a sled and has two concrete blocks to throw off the sled possibly, or go ice fishing, drop them straight down. But let's be physics oriented here and say Sarah wants to get off of the lake using the principles of conserving momentum. So we're going to have Sarah pick up one of the blocks and throw it off of the back of the sled. The mass of Sarah and the sled is 170 kilograms. Each cement block is 12 kilograms. So that gives us 24 kilograms for the cement, 194 kilograms for the system. At rest in the middle of the lake, no wind. Sarah doesn't have anything sharp to stick into the ice to push with, so have to use conservation momentum. Sarah throws off a block. Sarah can throw the block at a speed of 5 meters per second away from her. And it's going to go off in the horizontal direction. We're going to ignore vertical parts of the problem. It's not a projectile motion problem. We're just concerned in the horizontal direction as to what is happening. So we have 182 kilograms now with a sled and one cement block. It's going to be traveling to the right with some speed v. The concrete block traveling to the left with a speed of whatever the sled speed is, minus 5 meters per second. The minus sign, it's going the other way. Why does the sled move? Well, Sarah has created an object with momentum going to the left in this diagram. To conserve momentum, we have to have some velocity off to the right. So the momentum before the event takes place will equal the momentum after the event takes place. Before, the sled was at rest, so there is zero momentum before the event. After the event, we have 182 kilograms with velocity v1. We have 12 kilograms with velocity v1 minus 5. Again, important here, the velocity here is with respect to Sarah. Sarah can push this cement block not at 5 meters per second, but 5 meters per second away from Sarah. So as Sarah goes off to the right, as this push starts, the block will not have a full 5 meters per second back to the left. It's a relative speed, 5 meters per second away from Sarah. So ask your instructor. If I'm your instructor, ask me if you have a question on that concept. So we have momentum conservation, 0 before. Here's what we have afterwards when you distribute the 12 on v1 minus 5. We add 60 to both sides. We combine the like terms. We find that the speed of the sled in Sarah is 0.309 meters per second. Sarah is impatient. Sarah wants to get to the shore faster, at a faster rate than 0.3 meters per second. So Sarah picks up the second block and throws it in the same direction as the first block was traveling. Now we're just considering the system here of the sled, Sarah, and the one block. This one's out in space just for reference, but Sarah picks up another block and does toss it in the same direction. But Sarah is not tossing two blocks at once in part B of this problem. Sarah's just throwing the other block that was on the sled. So there is momentum beforehand. We're again doing conservation momentum. The system was 182 kilograms, 170 for the sled and Sarah, 12 kilograms for the concrete block. We knew the speed from part A, 0.309 off to the right. After the event here, we'll have velocity v2, 170 kilograms for the sled and Sarah, and then 12 kilograms, again traveling with respect to Sarah and at 5 meters per second away from Sarah. Again, it's important here that this velocity is with respect to Sarah. So if we do some distribution of the 12, we do a calculation and get a number over here on the left, add 60 to both sides, and divide by 182 now. The mass is different than the first calculation for our division. And we find the velocity v2 is 0.639 meters per second. 0.639 meters per second. If you notice, it's a little bit more than double. Why is it a little bit more than double? Well, we don't have as much mass for the sled and Sarah as we did moving to the right up here. So we've gotten rid of more dead weight, the concrete blocks, so we can travel a little faster as we continue to push concrete blocks off of here. So this is a little bit of a warm-up to rocket problems of pushing mass out the rocket motor, and the acceleration picks up because there's less dead weight of unused fuel as the fuel is sent out the nozzle. But conservation momentum applies, and Sarah has successfully exited the lake.